Negative charges move. That's what we see. And there was one more experiment. Interesting. What they said was, what does temperature tell us? Right? If we have a gas in this room, the temperature tells us how fast, on average, those molecules are moving. Right? Temperature tells us the average kinetic energy of the molecules. So let's take a piece of metal. It's got positives and negatives in there. One of those particles is free to move. Either the positives or the negatives are free to move around. And let's heat it up. And whatever's free to move is going to start moving faster and faster and faster. Well, what happens with the liquid? When you get the molecules in the liquid moving faster and faster and faster, pretty soon some of them are moving so fast they can break free of the way they hold on to each other. They can break free and they turn into a gas, right? That's boiling, evaporation. So let's take a piece of metal where we have positives and negatives and start heating it up. Eventually, something in there is free to move. Eventually, it's going to be moving so fast that it can break free of what's holding it into that metal. We can basically boil the particles out of the metal. And if you do that, electrons come off. So the electrons are free to move. So we've gotten several ways that we can tell that the negative charges are moving. All right? And an interesting one popped up here with the Hall effect and the way we measure magnetic fields, because it actually does tell us you can't make this substitution that negatives are going the opposite direction. You get a slightly different result. But for everything else we do, it works out. For our circuits and things, we can say negatives going to the left is the same as positives going to the right. All right, let's take a little break, and we'll continue talking about applications of magnetic fields. Normally we start at 11 o'clock, but I can be here a half hour earlier tomorrow, 10:30. Like 10:30 to noon, something like that tomorrow, if you're interested in a review session. So, circular motion. An interesting thing happens with these particles, right? Because the force is perpendicular to the velocity, let's make a magnetic field. What direction? Into the board? And let's have a positive charge moving with some velocity v. What direction is the force on my positive charge? To the left. So that means that at some instant later, if this is a snapshot in time, at some instant in time, a positive charge is moving towards the top of the page. There's a force on it to the left. At some instant later, where's it going to be? It's going to be over here somewhere, right? Moving this way. Because that force was acting on it. I could have maybe drawn an intermediate stage there, but... So eventually it's going to be over there. What direction is the force on it now? So at some instant later, I'll try to draw an intermediate one. It's over here, going this way. What direction is the force? At some instant later, it's on the left here, going towards the bottom of the page. The force is... So you see what we get. Circular motion. Because the force is always perpendicular to the velocity, it changes the direction of the velocity. It does not change the magnitude. It cannot change the magnitude of the velocity, but it can change the direction. And so if everything is just right and we get circular motion, we know something about circular motion. We know that the sum of the forces in the radial direction has to equal m acentripetal. Right, if there's circular motion, we know the net force in the radial direction has a special value, mv squared over r. And what is the net force in the radial direction? It's just the magnetic force. And the magnetic force is QVB. So what do we get? QB, I guess we really were looking for the radius maybe. So there's some applications here, like with a mass spectrometer. We can set up a situation where you have particles so you have a so you have an ion source, and it creates a positive charge. That positive charge is accelerated by this potential difference, and it enters. Maybe you'd also put a velocity selector over here, so you know that only a certain velocity particle is getting into your mass spec. But what you want to do is you want to have just a particular velocity coming in, and then you have a magnetic field over here. So the velocity is towards the top of the page, the magnetic field is out of the page, so the force is going to be to the right, and it's going to cause the particle to move in a circular path. And what we would do is we would put a detector over here. So if the particle's mass is just right, the radius is going to be mv over qb. Everything that comes in here hopefully has the same velocity. We know what the magnetic field is. We know that this is a singly ionized particle, so we know what Q is. And if it has the right mass, it ends up at our detector. And what do we do if we want to measure a different mass? We can change B and measure the signal from a different mass. So we can see what's in our gas over here that we're ionizing. Okay, so a mass spec looks to see how much of a particular mass you have in your sample. And it works on this principle.